Dear students, in today's lecture, we will try to create this table from scratch. Now, this single table will be more useful for you than reading an entire book. So, what is this table? What exactly does this table has? So, there on the top, you can see different processes: constant volume, constant pressure, isothermal, adiabatic, and polytropic process. And on the left hand side, you can see the different parameters like what is the PVT relation, what is the work done, change in internal energy, heat transfer, change in entropy, specific heat, uh, what is the index n, and change in enthalpy. So if you are able to fill up all this table, if you can create this table from scratch, if you are able to do it on your own and fill this table, then you will not face any problem in your entire thermodynamics. And then we will also learn how to draw the PV and TS diagram, which will be very, very important to understand the higher concepts in thermodynamics in jet propulsion. So without wasting any time, let us start. So we will start with ideal gas equation. Let us learn what is the ideal gas equation and what are the different forms it can be written in. Ideal gas equation. Now, many of us do study thermodynamics a lot, but we don't know the ideal gas equation properly. So the first way how we write the ideal gas equation is PV is equal to N R dash T. Now, what is N here? If you're writing it this way, what is N here? N is the number of moles. Number of moles. Whereas R dash is known as the universal gas constant, and its value is 8.314 kilojoule per mole Kelvin. And it is same for all gases, irrespective of what the gases are. It is same for all different gases. Now you can rewrite this equation as PV is equal to number of moles. Always you can write it by mass divided by molecular mass into R dash T. Now if we shift the molecular mass a little towards right, it becomes R dash divided by M into T. So this equation now becomes PV is equal to mRT, where R is equal to, R is the characteristic gas constant, R is equal to characteristic gas constant, and it depends, the value of R is dependent on the molecular mass. Value of R is dependent on, sorry, not M by M, it depends on the molecular mass. For example, let us consider the example of air. Do you know what is the molecular mass of air? R dash is going to be constant 8.314. Molecular mass of air is 29. So it becomes somewhere around 0.287, and the units will also change, kilojoule per kg Kelvin. And the characteristic gas constant will be different for different gases. Coming back to our equation, ideal gas equations, we have seen two different equations, right? PV is equal to nRT and R dash T, and PV is equal to mRT. Now we can also write it as P is equal to, if you take volume towards right and simply divide mass by volume, so it becomes this way. So P can be also written as rho RT, right? Where rho is nothing else but the density of the gas. Density. So you have seen that we have written the ideal gas equations in three forms, and we need to use all three, but mostly what you'll be using is the third form and the second form. Mostly what you'll be using This is the first form, first way how we can write it. This is the second way how we can write it. Now it depends on the question also, right? How the question has been asked. So it depends. So it is better to know all three and what are these parameters. Now having understood this, now let us move on to the next point of discussion, that is CP and CV. Now we have already done one CP and CV in our class. We have understood it. Let us try to understand it once again. Not in that detail, but in a different point of view. Now, whenever we are finding out heat transfer, we all know whenever we are finding out heat transfer, it can be given as mCV delta T for gases, right? Heat transfer for gases, mCV delta T if it is a constant volume process, or we can say Q is equal to mCp delta T if it is a constant pressure process. And this is something we have seen it in our earlier lectures. We have seen it in detail. So this is the value of Cp and Cv. This is what it means. Now, I'd like to introduce something very important here. For all gases, Cp minus Cv is equal to R. That is the characteristic gas constant. And the ratio of Cp and Cv is equal to gamma. Right? This is known as the ratio of specific heats. So these two equations are also very important if you want to solve all different types of questions in thermodynamics, and if you really want to recreate that lecture, recreate the first slide. Now let me tell you the value of gamma, right? The value of gamma is basically constant for if it is a monoatomic gas. So value of gamma is always going to be 5 by 3. 5 by 3 is equal to 1.67. And this is for monoatomic gas. For diatomic gas, for example, air we consider it to be diatomic because maximum it contains nitrogen and oxygen, right? So both of them are diatomic. One molecule contains two atoms. So for diatomic gases, the value of gamma can be written as 7 by 5, which is equal to how much? 1.4. And that is why we use 1.4 in all our equations, right? Adiabatic, reversible adiabatic or isentropic processes. And for polyatomic gases, right, gamma, the value of gamma is equal to 4 divided by 3. Right? This is from kinetic theory of gases. Okay, everything that you are studying is from kinetic theory of gases. That is equal to 1.33. So this is as per kinetic theory of gases. Everything that you have that is written here, right, from Cp, this and this, it is from kinetic theory of gases. So having understood this, okay, right, let us move on to the third thing before we start with the processes, that is the values of Cp and Cv once more, right? Now mathematically, we have seen it mathematically. Mathematically, we can write Cv is equal to change in internal energy with respect to temperature, or better to say del U, right? Del U by del T for constant volume process, right? But if you integrate it, right, you will always get that change in internal energy is equal to Cv delta T, if you're considering it to be small u, right? And if you're considering it to be delta U this way, or better to say, write it this way so that the handwriting is clear. Change in internal energy is equal to Cv dt or we can say delta U is equal to mCv delta T. So always remember the change, whatever the process might be. This is very important to understand. This is valid for all processes. Whenever you need to calculate the change in internal energy for whatever process it might be, it is always going to be mCv delta T for all processes. Now let us go back to our initial slide and check if it is true. Right? So here you can see change in internal energy. It is mCv delta T, mCv delta T, mCv delta T, mCv delta T, except for isothermal process. Why? Because isothermal process temperature is constant. And if temperature is constant, delta T is zero. So if delta T is zero, so definitely the change in internal energy will be zero. So otherwise, you see it is mCv delta T everywhere. Okay. Now, let us get back to our slide and try to calculate what can I talk about CT. Now this table, we are recreating each and everything. Again, mathematically we can say Cp is equal to del U by del T at a pressure is equal to constant. Right? So if we integrate it, right, this becomes del T is equal to Cp, sorry, my bad, del H is equal to Cp. Why am I writing dH here? This would be dH. Again, my bad. dH by is equal to Cp delta dt. Or if you want to write out change in enthalpy, total change in enthalpy, it is going to be m Cp delta T. So, and this is also valid for all the processes. The change in enthalpy is always going to be what? The change in enthalpy is always going to be mCp delta T for all processes. For all processes. Let us cross check with our table if it is true that change in enthalpy is same for all the processes. You can see it is mCp dt, mCp dt. Should come up to be mCp dt, sorry, mCp dt, my bad. And it is mCp dt 0 and mCp dt. So it is mCp dt for all the processes except for isothermal. So there was small mistake here. I'll correct it here. Right, adiabatic process, it is mCp dt, and for isothermal process it is going to be 0. For isothermal process it is going to be 0. Okay, because this was typed and I made a mistake in typing, but okay, I hope you have understood. So you see, if you have the basic concepts clear, then you can always get these things in the right order. So we have done what is change in internal energy, is change in enthalpy. Now let us go on to the processes one by one. Let us start from, say, constant volume process. Constant volume process. Now the constant volume process is also known as isochoric process, right? It is also known as isochoric process. Volume is equal to constant. Now, all of you, please look at me very carefully. So first of all, we will try to find out what is the PVT relation. What is PVT relation? What is the PVT relation for a constant volume process? Now we know PV is equal to mRT. Right? Now volume is constant, so I can write P divided by T is equal to mR by V. So this becomes mR by V is a constant, right? Because m is constant, R is constant, now V is also constant. So if that is the case, so the ratio of pressure and temperature will remain constant, P1 by T1. You change it, P2 by T2. If you change the pressure, this will always be equal to mRV, which is equal to constant. Which will always be equal to mRV, which will be equal to, which is going to be constant. So the correct PV T relation is P1 by T1 is equal to P2 by T2. So let us go back and see if it is written correctly. So constant volume process, or you can say P2 by P1 is equal to T2 by T1 is the same thing as this. Same thing as P1 by T1 is equal to P2 by T2. You can write it as the same equation. Okay. Now let us try to see what is the heat transfer. We have already found out what is the change in internal energy, right? We can find out what is the work done. Work done. Second point is the work done. Let us try to find out what is the work done. So if you want to find out what is the work done, we all know generally what we are calculating is the PDV work, that is the displacement work, that is we are trying to calculate the PDV work, that is the displacement work. So the work done can be written as integration of PDV from 1 to 2. So this becomes P V2 minus V1. So work done is equal to P V2 minus V1. And for constant volume, right, it is going to be 0. Why? We are looking at which kind of process? We are looking at constant volume process. V is equal to C. So for if the volume is constant, right, so the work done is going to be 0. The next thing we need to calculate is, so let us quickly check if it is 0 in our first slide. So you can see work done for a constant volume process is 0, change in internal MCV/dt. Now let us try to find out what is heat transfer. Let us try to find out what is heat transfer. Heat transfer. Now we all know that heat transfer by the first law of thermodynamics, it is equal to change in internal energy plus work done. Okay? Now change in internal energy for any process is mCV delta T, and work done in this case you can see for constant volume process is 0. So I can say that the heat transfer for a constant volume process can also be given as mCV delta T, and it is something we already know, we have already seen, right? This is something which we have already seen when while doing one of our previous slides. This is how we say the heat transfer is given, right? So heat transfer is equal to mCV delta T if the process is constant volume process. Now let us try to find out what is the change in the entropy. What is the change in entropy in a constant volume process? So this is going to be our fourth point. change in entropy, that is delta S. Let us try to calculate. Now, last class we have seen that delta S, the value of delta S can be written as, the change in entropy can be written as, there are three equations in fact. It can be written as CV ln T2 by T1 plus R ln V2 by V1 or it can be written as CP ln T2 by T1 plus minus R ln P2 by P1. So we can use the first equation, V2 and V1 are same, right? So V2 by V1 becomes 1, so this equation becomes 0. So I can say that delta S, the value of delta S can be written as, simply written as CV ln T2 by T1. Let us cross check in our first slide if it is CV ln T2 by T1. So constant volume process, yes, and change in entropy can be written as mCV ln T2 by T1. Right? Specific heat is CV, we know this, index N. So let us try to find out what is index N. Now, if any process, all the processes, if they are represented PV to the power N is equal to constant, if this is how we represent any process, so what is the index N? So that is the question, what is the index N? And this will be required, this equation will be required because we represent all different processes using this P V to the power N is equal to C. Now if volume is constant, right, so whatever, so volume is constant, so I am writing it this way, V is equal to C by P to the power 1 by n. Just try to see this. Now C 1 by n, not 1 by 2, 1 by n. Now this can be written as V is equal to C to the power 1 by n, which is also a constant, right? Because C is constant, divided by P to the power 1 by n. Now this is already a constant. Right? So volume can be constant only if P to the power 1 by n is 1, equal to 1. And P to the power 1 by n should be is equal to 1. This is only possible if 1 by n is equal to 0, and this is only possible if n is equal to infinite. N is equal to infinite. So always remember, for a constant volume process, what is the value of n? N is equal to infinity. Let us check in our first slide if it is n is equal to infinity, and that's true. So you see, we have done the first column, that is for constant volume process. Similarly, let us try it for constant pressure process, and we will try everything fast. We'll try everything fast so that we can just finish up this lecture in just another 10-15 minutes. So let us now try to, having understood the constant volume process, let us try to understand constant pressure process. Constant pressure process. Let us try to understand for constant pressure process. So it is also known as isobaric process, right? So the first is the PVT relation. So PVT relation. Now we all know PV is equal to mRT, right? Pressure is constant. So what I'll do, V by T is equal to mR by P. So this becomes constant. Right? So what I can say, always V1, the ratio of V1 by T1 will always remain constant. The ratio of V1 by T1 will always remain constant, V2 by T2. Right? It is always going to be mRP because it is constant. So this becomes our PV relation, PVT relation. So V1 by T1 is equal to V2 by T2. So this is our first thing. The second thing we need to find out is what is the work done, work done. Now work done, we all know work done is equal to integration from 1 to 2 pdv. Here pressure is constant, so I can simply write p integration of dv from 1 to 2. So this can be written as p v2 minus v1. This is very, very simple calculation of work done, and we have seen calculation of work done even one of our previous slides. Right? The third thing that we would like to look is the change in internal energy. We have already done. We have seen that is mcv delta t. Let us consider what is heat transfer. Heat transfer. Let us consider what is heat transfer. So heat transfer dq is equal to, we can write it as change in internal energy plus work done. So heat transfer can be change in internal energies mcv delta t plus work done is equal to p v2 minus v1. Now we'll not be able to calculate it this way. Okay, let us try to have another approach for this. So we all know h is equal to u plus pv. Now if you differentiate h, it is going to be du plus pdv plus vdp. Right? Once you will differentiate v keeping p constant, and then once you will differentiate p keeping v constant. Right? Now, if you see this equation, right? du plus pdv. What is du plus pdv? Du plus pdv, right? We have seen it earlier. Pdv work. Pdv work is nothing else but it is a displacement. So du plus pdv. Yes. Can I say it is nothing else but mcp delta t? Or if you're finding it difficult, let us say it this way. Okay, let us look at here. Right? Let us look at here and try to understand this. Right? So dq is equal to du plus w. Right? So this is also is equal to du plus what is w? The work done, that is pdv. So can I write du plus pdv is nothing else but what? dq. And if the pressure is constant, can I say dp is equal to 0? So the heat transfer, it is coming out to be how much? dq is equal to dh, change in enthalpy. And we all know what is the change in enthalpy? That is mcp delta t. So here the heat transfer is going to be change in enthalpy, and that is equal to mcv delta t, delta h cv delta t, or I can say total heat transfer is equal to mcv delta t. Right? So this is important to understand. So let us go back to our slide and see if the things are same the way we have discussed. So v1 by v2 is equal to t1 by t2, right? P is equal to v2 minus v1. Yes. Change in internal mcv dt. Heat transfer is equal to mcp delta dt. So this, you see, constant volume process heat transfer is mcv dt, and constant pressure process heat transfer is mcp dt. This is something we already know. Now we have also proved it. Okay. Now let us try to calculate what is change in entropy. What is the specific heat? Specific heat, you already know that it is Cp, index N, and change in enthalpy is something we have already calculated. So let us calculate. There are two things remaining now. Let us try to calculate them for constant pressure process. So now what we are going to try to do is we are going to try to calculate change in entropy. Change in entropy, which is equal to delta S. So delta S, we can always write it as m Cp ln T2 by T1. This is the equation we have seen, minus m R ln P2 by P1. Now this is a constant pressure process. If it is a constant pressure process, P2 by P1 will be 1. So ln 1 is 0. So delta S can be written as mCp T2 by T1. So talking about the coefficient n, the index n. Now P v to the power n is equal to constant. Right? This implies P is equal to constant divided by v to the power n. Now we all know this should be constant. Now this can only be constant if v to the power n is equal to 1, right? So for v to the power n is equal to 1, the value of n should be equal to 0. So always remember, for a constant pressure process, the value of index is always going to be 1. So have we recreated all the points here? Yes, we have recreated this, 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 this. Okay. Now let us try to do it for isothermal process. Let us be quick. We are already 30 minutes. Let us quickly do it for the other processes also. Isothermal process. So let us quickly try to figure out what will it be for isothermal process. Iso process. Isothermal process means temperature is equal to constant. Now, all of you, we'll also have to draw the PV diagram. We have to understand how to draw the PV diagram also. So it is going to take some time, but nevertheless, we'll try to make it as fast as possible. Now we know PV is equal to mRT. Now if the temperature is constant, what I can say, P1 V1 is equal to P2 V2 is equal to mRT is equal to constant. So the equation, the relation between pressure, volume and temperature reduces to P1 V1 is equal to P2 V2. Right? Now if you want to calculate what is the net work done, let us try to calculate what is the work done. Let us try to calculate what is the work done. Now the work done can be written as integration of P dV. Now pressure we can write from this equation. Now we all know that P into V is equal to constant. So how can I write pressure? I can always write pressure is equal to C divided by V. Right? So this becomes integration of C by V dV. C is nothing else but constant. So if I take the constant out, so this becomes ln V from 1 to 2. If I'm taking the process from 1 to 2, so this becomes C ln V2 by V1. Now what is the value of C? Now C is the constant. I can write P1 V1 is equal to P2 V2 is equal to PV is equal to mRT is equal to constant C. All these are equal to constant C. Array, this is the equation, na? Right? P1 V1 is equal to P2 V2 is equal to mRT is equal to constant. This is what the constant C is. Right? So what I can write, the work done is nothing else but it is equal to P1. I can write it the way I want now. I can write it as P1 V1 ln V2 by V1. If you want to add mass, you can add mass also. So mass will not be added here, by the way. It is equal to P2 V2 ln V2 by V1 is equal to mRT ln V2 by V1. Now you can also replace V2 by V1 by P1 by P2. You can always rewrite this equation, right? V2 by V1 is also is equal to P1 by P2. So you can also write this equation by changing what V2 by V1 into P2 by P1 by P2, and you will again have the same answer. So let us go back. So I have only written one, right? P1 V1 ln V2 by V1. So I marked it as star. So you now know that there you can write it in many different forms. Change in internal energy is 0. Right? Now work done. Now if you say heat transfer will be same as that of the work done. Why? Because heat transfer is change in internal energy plus work done. Change in internal energy is 0. So heat transfer is nothing else but equal to work done. Let us try to calculate what is change in entropy. Right? Let us try to calculate what is change in entropy. Now I think you have already understood how to calculate a change in entropy. It is not going to be very difficult, and we will also try to figure out what is the index M quickly. Change in entropy. Delta S can be written as m Cp ln T2 by T1 minus R m R ln P2 by P1, or it can be written as m Cp ln, the first term remains same, T2 by T1 plus m R ln V2 by V1. So here temperature is constant, so this becomes 0, so this becomes 0. So there will be two equations for delta S. The way you want, you can write it, right? You can write delta S is equal to mr ln P2 by P1, or you can write it as plus mr ln V2 by V1. Finally, let us try to figure out what is the index N. Index N. Now, if you write the equation P V2 to the power N is equal to constant, right? Now isothermal process, we know P V is equal to M R T. It is already equal to constant because M is constant, R is constant, T is constant. So if you compare these two equations, you'll get the value of N is equal to 1. So for isothermal process, the value of N, the index N, is always going to be 1. So hope I have recreated the entire slide. Yes, we have done it. So let us finally figure it out for adiabatic process, which is very important. So let us go back to our adiabatic process. So let us try to create it for adiabatic process also. Now for adiabatic process, this is very important. Now, reversible adiabatic process are also known as isentropic process. Always remember, right? Isentropic process where entropy is 0. We have seen it in last class. Reversible adiabatic process means isentropic process. So change in entropy is equal to 0, and this is the same slide that we are going to use. So isotherm adiabatic process, you can see the change in entropy is going to be 0. So let us calculate what is heat transfer. I might have miscalculated it. What is specific heat? Specific heat is going to be 0. Heat transfer adiabatic process, yes. For it is a adiabatic process, so definitely the heat transfer is going to be 0. Change in entropy is 0 because it is also a reversible adiabatic process is the isentropic process. Change in entropy is 0. Right? Specific heat is 0. Why? No heat is being supplied, right? So we cannot increase the temperature, right? So that is why the specific heat is going to be 0. Now for isothermal process, the specific heat is going to be infinite. Why? Because no matter how much heat you are supplying, the temperature is constant. No matter how much heat you are supplying, the temperature is constant, and that's why the specific heat for isothermal process is going to be 0. Right? Now let us first, these equations are very, very important. Let us first try to create the PVT relations for adiabatic process, and then we'll recreate the equation for work done, and rest of the things are pretty much same. Right? Rest of the things are pretty much same. And the index N is going to become gamma, which we already know it is equal to Cp by Cv. Let us try to now go back to our adiabatic page and try to form the equations. Right? Now, the first thing that we are going to do is you create the PVT relations. PVT relations. This is important. pressure, volume, and temperature relations. Adiabatic process is the most important because in most of the, you take Brayton cycle, you take steam cycle, Rankine cycle, or any other cycles, the most of the processes will be reversible adiabatic process, the ideal processes. At least two processes will be there. So what are PVT relation? Now, first of all, we know that PV is equal to MRT. So PV by T is equal to MR. So MR is constant, so I can say this is equal to constant. So this itself I can recreate. P1 V1 by temperature T1 will remain constant. P2 V2 divided by T2. So the ratio P1 V1 by T1 and P2 V2 by T2 will remain constant for an isentropic process, reversible adiabatic process, or you can simply say reversible process. So this is the first thing. Now, again, let us take the volume from here, right? Let us take the volume from here, from this equation, and try to substitute it here in this equation. We can always say volume is equal to mRT by P. Right? If you substitute it in this equation, or let me do one thing. Let me make it even easier. Now, all the adiabatic processes are represented PV to the power gamma is equal to constant. Where gamma we have already seen, it is the ratio of specific heat capacity Cp by Cv. All the adiabatic processes can be represented this way. So these are experimental. These are all experimental things. Right? So if you see, if I say from here, I can say P is equal to C to the power C divided by V to the power gamma. If you replace P in this equation, what you will get is a relationship between V and T. You can do it and see, right? If you replace P in this equation by C divided by V to the power gamma, you will get a relationship between V and T, and that will be like V1 by V2 to the power gamma minus 1 is equal to T2 by T1. Okay, and similarly, if you can write V is equal to C divided by P to the power 1 by gamma. You can replace V in the same equation and you will get a relationship between pressure and temperature, which will be like T2 by T1 is equal to P2 by P1. These equations are very important, especially this one, gamma minus 1 by gamma, because while doing Brayton cycle, you are going to use all these equations repeatedly, right? While trying to solve for the numericals there, this equations will be frequently required. So let us see if our slide contains the same thing as that we have spoken here, right? So yes, P1 by T1 to the power 1 by gamma, this one of the equations. Okay, we have not created this equation. T2 by T1 is equal to P2 by P1 to the power not n minus 1, gamma minus 1 minus divided by gamma. P2 by P1 is equal to V2 by V1. This is equation we have created. And these two other equations also you can definitely create it without much problem. So let us now try to create work done. Let us now try to create what is the work done for a isothermal process. Let us try to create what is the work done for a isothermal, for an adiabatic process. So work done, this is, if you can understand, that is going to be pretty good. Now work done is always given by the displacement work I'm talking about. It is given by integration of P dV, right, from 1 to 2. Now I can always write pressure, right, as for an adiabatic process C divided by V to the power gamma dV. from 1 to 2. Let me see. Now if you do this, C is coming out inside. It is simply becoming, if you integrate it, so I'll write it like this: integration of v to the power minus gamma dv, right, from 1 to 2. Now if you try to integrate v to the power minus gamma, c is constant, so it is simply becoming v to the power minus gamma plus 1 divided by minus gamma plus 1. So it is equal to c v to the power gamma 1 minus gamma divided by 1 minus gamma. Now what is c? C is nothing else but a constant. It is equal to P V to the power gamma. We can also write it as P1 V1 to the power gamma. We can also write it as P2 V2 to the power gamma, right? You can write it the way you want, right? This is from 1 to 2, 1 to 2. So this becomes C V2 to the power 1 minus gamma minus V1 to the power 1 minus gamma divided by 1 minus gamma. So if you simply multiply C inside, so this equation becomes V2 by V1, or P1 V2 V1 P2 P, or let me write it as work done is equal to P2 V2 minus P1 V1 divided by 1 minus gamma. If you multiply it minus sign up and down, it will become P1 V1 minus P2 V2 divided by gamma minus 1. Right? And this is the same equation that we are seeing here. You see P1 V1 minus P2 V2 by gamma minus 1. So once we have done this, now polytropic process. What is polytropic process? Try to understand. We say P V to the power n is equal to constant. If value of constant n is equal to infinite, it is constant volume. If n is equal to 0, constant pressure. N is equal to 1, it becomes isothermal process. If n is equal to gamma, it is adiabatic process. If n assumes any other values apart from this 4, it is a polytropic process. So derivation of polytropic process is very, very simple. What you simply need to do is simply replace gamma by n, and you get each and everything, the same things, you will get it here. The same thing, you will get it here. Right? So I'm not separately deriving it for polytropic process. The only thing that you can note down is the specific heat for a polytropic process can be given like this: NCV minus Cp divided by n minus 1. Right? And so that is the only thing that you really need to know. Right? And apart from that, everything is fine. So if you have understood this, so we are already 48 minutes down. Let us quickly try to create the PV diagram as we have spoken at the starting of the class, without which the class will not be complete. Right? So it is not going to take much time. If you have understood it till this point, then understanding the PV diagram and TS diagram is not going to take much time. We can quickly do it. Okay, we can quickly do it. So let us start with the PV diagram. The x-axis is the volume, and the y-axis is the pressure. So I'm taking up processes. Now watch me. If volume is equal to if the pressure is equal to constant, definitely this is going to be a straight line like this, horizontal line. If volume is equal to constant, this is going to be a line like this. So I don't have any problem in this. Pressure is equal to constant. See, pressure is equal to constant will be a horizontal line, right? Everywhere the pressure is constant. So volume is equal to constant will be a vertical line. So I don't have any problem in this. Pressure is equal to constant. So if I see this is n is equal to what? For a constant pressure process, the value of n is going to be 0, right? And this is volume is equal to constant, so the value of n is going to be infinite, right? So we are left with two more lines. So what are those? One is the constant temperature isothermal process, and one is the adiabatic process. Let me say this is the isothermal process, and the red one is the, it will all pass through the same point. Okay, um, though my drawing looks a little bit shady here, it is, now it looks good. So it is going to pass through the same point, all of them. Okay, so always remember, so see, this is going from n is equal to 0 to n is equal to infinity. You can always remember, so this is going to be n is equal to 1. And what is n is equal to 1? That is temperature is equal to constant, isothermal process. And then will come n is equal to gamma, because the value of gamma, we have already seen, the value of gamma is greater than 1. The value of gamma is greater than 1, and that is why this is going to be gamma, n is equal to gamma, that is adiabatic process. So if you come this way, it is going to be this side. If you go, this is how the graph will look like. This is how the graphs are going to look like. It is representing all the constant pressure. So this is very important, right? So when you are increasing the volume, when you are expanding, the pressure will reduce. So in the fourth quadrant, you can see the volume decreases as the pressure, also volume increases as the pressure decreases. In the third quadrant, you can see this is a compression process. So this is representing compression here, right, where volume is decreasing and pressure is increasing. This is the expansion. This is the expansion process. So this is very, very simple. This is the PV diagram. Okay, and it's not very hard to create. It only requires some amount of practice. Let us now try to create the TS diagram. Let us try to create a TS diagram. So temperature on the y-axis and entropy on the x-axis. Now constant temperature process will be the blue horizontal line, right? So not a problem here. This is temperature is equal to constant, right? And the constant entropy process is going to be this. Entropy is equal to constant. So entropy constant means adiabatic, and temperature constant is isothermal, right? Now here the expansion process or compression process will be in the second quadrant, or the fourth quadrant, depending on you are supplying heat or you are rejecting heat, right? And the graphs will look like this. This is one of the graph, right? There are two more processes to be shown, and polytropic process will be any other process except for these two process. So can you tell me what will be this process? N is equal to what? And for this process, you can always think it this way. The heat transfer, now you know that heat transfer can be said to be mcv delta T, or is equal to mcp delta T. This is constant pressure process, constant volume process. Now heat transfer will be always be greater for constant pressure process. Why? Because Cp is greater, right? Cp is greater. So, and we know from the last class that heat transfer is nothing else but the area under the graph. Now, if you look at both the graph, which area is going to be greater? The area of the red one is going to be greater. So this is going to be n is equal to 0, that is pressure is equal to constant. And for n is equal to C, so this is nothing, n is equal to infinite, that is volume is equal to constant for the upper graph. So this is how the PV graph, the TS diagram will look like. On the first quadrant is heat supplied, right? On the fourth quadrant is heat rejected. So this is what it is, right? This is what it is, the TS diagram, and we will need these diagrams while learning the cycles. So that's all for today. Thank you all of you. I hope it was useful for all of you, and please make sure you comment in the chat box. What did you like about it? what do you want to improve, and how can I help you even more with these lectures. Thank you. Bye bye.